Welcome. Today we're going to talk about the new Attero-100G, which is the one and only 100 gigabit Ethernet impairment solution on the market today. I'll repeat that again, it's the one and only 100 gigabit Ethernet impairment solution on the market today. So what's the key problem that we're trying to solve? The problem is that network latency kills throughput. It's a big issue in the networks. Latency itself is caused by propagation delay, switching routing and buffering queuing. Now Amazon, Netflix, YouTube all use TCP for streaming video, which is pretty much the bulk of the internet traffic in the Western world. Now this is different to video transmission in the past, which is UDP. UDP itself is not affected by latency. So the issue is that latency kills TCP throughput. In TCP there's an acknowledgement process. TCP waits for acknowledgement packets before sending the next packets, which is affected by a delay. TCP also has a windowing technique which slowly ramps up the number of packets transmitted and is also greatly affected by latency. And if packets are dropped, then retransmission is needed, and this process is also again affected by latency. So as a result, you need to simulate the network in the lab to see the effect of latency on the service your equipment or network is carrying. You need to be able to add delay to test the impact on throughput. You need to error packets and measure the impact on throughput due to packet loss. Now some say you could use large drums of fibre to simulate the network, but there are problems with that, as you'll see with this slide. Drums of fibre are not the answer for a number of reasons. First of all, they're way too big. They're too expensive, there's a lack of control, and they need amplification. So in terms of being too big, they're extremely large, heavy and unwieldy. 200 kilometres of fibre is needed for 1 milliseconds of delay. The distance from LA to New York is 22.5 milliseconds of delay, that's 4,500 kilometres. So that's 22.5 drums of 200 kilometre fibre to simulate that distance. It's way too expensive. 1 milliseconds of fibre is costing the web at around $260,000. Now the cost of doing that from Los Angeles to New York would be 22 drums of that sort of fibre, so that would be $6 million, which is prohibitively expensive. There's a lack of control. In other words, if you want to test the point of failure, it's not easy to adjust the length of the fibre. Splicing fibre is a one-time only event. You can't easily switch in and switch out delay values if you're using drums of fibre. And adding additional drums is also problematic. 1310 nanometers of fibre drum at a loss of 0.4 dB per kilometre means you've got an 80 dB loss for 200 kilometres. Now a 100 gig LR4 transmitter only supports up to 100 kilometres, so amplifiers are needed just for that one drum of fibre for greater than 100 kilometres. So that's more cost and more complexity, and if you've got additional drums, that's even more amplification, more connector issues, more losses, etc, etc. So the solution to this problem is the Attero-100G. For latency, you're able to emulate delay-sensitive TCP traffic. You're able to emulate delay critical data for financial services, and with full line rate delay of up to 256 milliseconds at 100 gig and 640 milliseconds at 40 gig. There's repeatable, precise adjustment of latency to test design margins and tolerance, and there's no need for large, costly reels of fibre with large uncertainty and lack of control. You can add impairments by introducing lost, misordered and errored packets, adding repeated packets, and for interfaces you've got 100 gigabit Ethernet, CXP, CFP2, and for 40 gigabytes you've got QSFP plus interfaces. So just to recap what we said earlier about TCP and latency, many folks believe that video streaming was carried over UDP. However, this is no longer the case. Most of the streaming video on the internet uses TCP. So Netflix, YouTube and Amazon all use TCP for streaming video, which is most of the video streaming in the Western world. Therefore, these important services can be affected by delays in the network, as TCP is a reliable protocol and will retransmit data until received correctly. So the consequence is that delay is extremely important for video, which means that significant retransmission can occur due to network problems, and this is made worse by long transmission delays. Now, one of the reasons given for this switch from UDP to TCP is that content providers want TCP for reliability, quality of picture, etc. And providers believe that today's networks are much higher bandwidth and therefore able to cope with the longer delays in retransmission. However, all of that needs to be verified, and the Attero-100G is a way to simulate these long delays. Now, latency is such an issue that on some satellite links have even implemented TCP spoofing to pretend that the link's terminated earlier than it actually is, to pretend that it's got lower latency or lower delay. This gives you an example. We talked about TCP windowing earlier. This shows you how windowing works. The sender sends out one packet, it waits for the acknowledgement before doubling the number of packets and then repeats. Now when a packet is lost due to congestion, then the sending rate is halved. And there's a slow start kicks in again, but this time it won't double the rate, but it increases more slowly a segment at a time. And this is done to detect the optimal throughput. Now this whole process is extremely sensitive to delays throughout the network. This graph here shows the effect of latency and throughput. The first section left shows the effect of windowing with just 30 milliseconds of round-trip delay. Now you can see the data is constantly halted as the window size is full, and then the sender needs to send the acknowledgement packets back again. Now on the right hand side, with the exact same bandwidth but with the latency increased even further to 256 milliseconds this time, the throughput drops dramatically, even though the bandwidth of the link has not decreased in the slightest. This graph shows the effect of 0% packet loss on the left with almost full bandwidth utilization. Then the next graph shows it with 3% packet loss. Congestion control starts to kick in with the slow start process, and you start to struggle to get data to fill the link, even though there's no latency. And then with the next section of the graph, when you add 30 milliseconds latency, combined with that 3% packet loss, that further impacts the throughput, leading to lower link utilization. And lastly, on the right hand side, with 3% packet loss and 250 milliseconds of round trip delay, then there's almost no throughput whatsoever. Now UDP itself is unaffected by latency, as we said earlier. So with 3% packet loss and latency changing from 0 milliseconds to 30, then to 256 milliseconds, there is no change in the throughput at all. However, the issue with UDP is you don't have the same quality of service and reliability on the data that's sent to the other end. So in summary, latency kills TCP throughput. It's caused by propagation delay, routing and buffering delay. Streaming videos now carried by TCP, Netflix, YouTube, BBC iPlayer, Amazon, etc. A TCP relies on establishing a connection via handshake and acknowledgement process. And throughput is greatly affected by the latency and packet loss in the line due to the retransmissions, etc. So the solution is the Attero-100G emulates delay critical data for financial services, emulates delay sensitive TCP video traffic, and you've got repeatable precise adjustment of delay to test design margins and tolerance. And there's no need for large reels of fibre with large uncertainty and lack of control. So basically with the Attero-100G you have a real network in a box. You're able to test applications, protocols or devices against real network conditions using network emulation. So you can conveniently test your application, services, protocols or devices against a wide range of delay, bandwidth and impairment conditions found in real world networks. The advantage over the traditional testing approach is it avoids the wait and see approach to validating against real world environments. It saves the time and cost of building inflexible and unrealistic networks, and it's non-intrusive. It avoids the necessity of troubleshooting on the production environment. It's also a repeatable test methodology. You're able to compare meaningful results with colleagues and customers. And it introduces real world conditions as early in the development cycle as possible to save headaches further down the line. In summary, network emulation complements your existing generator analyzer test equipment arsenal. So here you see the new Attero-100G on the right, which is the new platform for 40 gigs and beyond, with Attero-X on the left, which is the platform for up to 10 gigabit Ethernet. This is a bit bigger picture where you're able to see all of the connections, the optical connections down here on the bottom left. And we also have an updated user interface with a new look and feel. Got a web-based GUI approach with a built-in controller. And you've got easy port selection and interface setup. In terms of optical interfaces, we support CFP2 interfaces for 100 gig Ethernet SR4 and LR4, so that's 4 wavelengths of 25 gigs. You've got CXP SR10 interfaces for 10 fibers of 10 gigabits, and you have QSFP Plus for 40 gigs, which is 4 fibers of 10 gigabits for 40 gigs. In terms of functionality, drop 1, we've got full line rate delay, single flow in each direction with errored packets, supporting up to 256 milliseconds at 100 gigs, up to 640 milliseconds at 40 gigs, We'll follow up a quarter later with packet corruption, drop packets, repeated packets, and filter builder, and then drop 3 will add additional functionality in the following year. Thank you.